Hello, and welcome to another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and today we're going to be doing Unit number 2, Lesson number 5 on continuity and piecewise functions. These are two very important topics in the course. We're introducing continuity really for the first time, although piecewise functions are certainly something that you've seen in previous courses. So, let's jump right in and define continuity using a very understandable geometric definition. Alright. The geometric definition of continuity. A function f of x is called continuous at a point in its domain, x equals c, if the function can be drawn at this point without lifting up your pen or pencil. A function is called continuous over an interval, a to b, if it is continuous at all values of x on this interval. Alright? So it's very simple. If I can go from point A to point B without ever picking up my pen or pencil, we're going to say that the function is continuous on that interval. If I can't do that, then we're going to say it's not continuous on that interval, and we're going to talk about what are known as discontinuities. So take a look at exercise number 1. Which of the functions pictured below is continuous over the interval a to b? Alright, well hopefully you chose choice 3, right? If I start at A and I move to point B, I never have to pick my pen up. On the other hand, if I look at exercise or choice 1, right, I'm moving my pen along, I have to pick it up to skip over that missing point, and then I can continue along the way. This is what's known as a discontinuity. A discontinuity, that's supposed to be a C there. All right, an X value where I have to pick up my pencil. Likewise, we also have a discontinuity right here because I have to draw, I approach this vertical asymptote, I have to pick up my pencil and put it back down to finish it off. Same thing here, right? There's really only one difference between choice 1 and choice 4, which is I have to pick up my pen, put it down here, and then pick it up again to finish. Again, another discontinuity. Okay? So actually being able to think about where a graph is continuous and where it has discontinuities is relatively easy from a geometric perspective. Later on, we're going to have an algebraic definition, not in this lesson, but later on we'll have an algebraic definition that allows us to think about continuity from a completely algebraic perspective. For now, though, pause the video if you need to write down anything you have to before I clear out the text. Okay, here it goes. All clear, and moving on. All right, let's take a look at exercise 2. It says the function f of x equals 1 divided by x minus 2 plus 1 is defined over the interval x is greater than or equal to negative 2, less than or equal to 5. Sketch the function below and state any values of x at which the function is discontinuous. All right. Well, why don't you pause the video now and attempt this problem on your own, and then we'll go through it. All right, let's do it. Well, recently we looked at functions that you absolutely positively need to know, and this is based on one of those parent functions, right? This is based on the parent function y equals 1 over x. And of course, y equals 1 over x has been shifted to the right 2 and up 1. All right, I'm going to actually just get rid of that so that we can see it a little bit better. Okay, I think what I'm going to do is I'm going to use my prepackaged lines to create some axes, all right, in red apparently. Then remember how I do this. What I'm going to do is I'm going to shift 2 units over and shift 1 unit up. And now I need to pay attention to the fact that this is my domain, okay? They've given me the domain. All right, I should only graph over that. So what I'm going to do is I'm going to graph 1 over x, but I'm going to do it in dashed, and then I'll come back in a little bit and I'll sort of flesh it out. All right, so negative 2, let's say is right there. That's where my function starts. right? And then it goes all the way to 5. 3, 4, 5. So that's the only portion that should be colored in. Now, clearly, it's got a discontinuity at x equals 2. In other words, if I started drawing it from -2 to 5, right, it's at x equals 2 that I would need to pick the pen up to complete the graph. All right? So, two skills put together, being able to identify a parent function, its shifts, and graph it, along with the thought of discontinuities. All right, well, I'll pause the video now, and then I'm going to clear out the text. Okay, here we go. Excellent. Let's take a look at piecewise functions. Now, a lot of people kind of think of piecewise functions as cheating, all right, because they're not defined with just a single algebraic formula. In fact, they're defined with different algebraic formulas for different parts of their domain. I don't think of them as cheating at all. In fact, if I look at the strict definition of a function is a rule that gives an output, at most one output for a given input. There's nothing about that definition that implies that the function has to be defined with only one equation. There's nothing that says that it has to be a simple rule, right? It's just a rule. So let's review some things about piecewise functions. All right. Take a look at exercise number 3. I have a piecewise function defined using this formula. Now, the first thing you have to be able to do with any function, regardless of whether it's piecewise or not, is you have to be able to evaluate that function. In other words, you have to be able to give outputs for different inputs. And that's letter A. It says evaluate f of -3, f of 0, and f of 4. Pause the video now and see if you can remember how to do that. All right. Well, to evaluate f of -3, we have to know which formula I use. But the whole point of this is that the function's rule is 2 times x minus 1 if the x value is less than 0. Well, -3 is less than 0. So I apply that formula and I get f of -3 is -7. Skipping for a moment to f of 4, right? Well, again, I look at this. 4 falls into this category, so I have to use this formula. So I'll get 4 plus 3, and I'll get a +7. Total coincidence there. Now, f of 0. Well, we have to see which one of the formulas applies. And it's this formula again, because there's the equals 0. So 0 plus 3 gives me 3. All right. So the most basic thing that you need to be able to do with piecewise functions is simply evaluate them. And it's all about just saying, hey, look, I need g of 7. Which formula applies when x is 7? So it's not too bad. All right, but let's take a look at letter B. Letter B asks us to draw a sketch of f of x. So I'd like to draw a sketch of this function. I'm going to draw a couple axes, all right? And I'm going to show you the way that I talk to students about sketching piecewise functions. To begin with, I ignore the intervals, generally ignore the intervals, unless there's something that really strikes me about them. And I say, well, okay, I know that's a line. Okay, I'm going to erase this over here eventually. But I know y equals 2x minus 1 is a line, right, with a slope of 2 and a y-intercept of -1. So I just sketch that, okay? I put a little y-intercept of -1, and I sketch it in dashed. All right. Like this. I don't worry about it at all. I just put it in dashed. Then I look at y equals x plus 3. That's a line with a slope of 1 and a y-intercept of 3. So I'm going to graph that as well. And I'm going to graph that in dashed. All right. Now remember, the cutoff point here is x equals 0. And that line 2x minus 1, well, that applies everywhere. Actually, I need to erase this. Ooh, that didn't work out well. Sorry about that. Let me try to get my axes back in there a little bit. It's not the best thing on earth, but we'll live. I need to apply this line for all values of x up to, but not including, so that's an open circle even though it may not look like it, up to x equals 0. Remember, it's x equals 0, not y equals 0, x equals 0. And then my other function, closed circle, right, takes off from there on out. This is one of the least impressive piecewise graphs I've ever seen. At the end of the day, it should look kind of like this. Something like that. All right, sorry if mine doesn't look that great. Okay, now what should be obvious is that it has a point of discontinuity. So to answer letter C, it's got a discontinuity at x equals 0, right? Because if I was graphing this thing, I'd have to pick my pencil up at that point, put it back down in order to finish the graph. All right? That's how you graph piecewise functions. We'll get some practice in the next exercise as well, but pause the video now if you need to write down any of this. All right, clearing out the text. All right, exercise number 4. The piecewise function y equals g of x is defined over the half interval. Actually, it's not a half interval. My apologies, I changed that to a full interval because I do have the 2 included by the formula given below. Sketch this function, so it's actually what's known as a closed interval. Sketch this function and then list any values of x in the interval -3 to 2 where the function is discontinuous. All right, well, this is a more complex piecewise function, and yet I still would like you to pause the video and see if you can sketch it for yourself. Okay? All right, let's go through it. Gonna give myself some axes. Okay. Now again, I'm not going to worry about the domain interval. I'm just going to look at that. And I'm going to think to myself, what is this the graph of? Now that could be the trickiest part of this problem. This is a semicircle, right, with a radius of 3, and it's the lower half. All right, so let's graph that. 1, 2, 3. Remember, what I'm going to do is I'm going to graph it in dashed. We'll fill it in later. So it looks something like that. Now for a moment, let's skip that, whatever that is. Let's talk about this. Now y equals 4 minus x squared, that's a parabola, right? That's a parabola that opens downward like this, and it's been shifted up 4 units. So 1, 2, 3, 4. And remember, it would have x-intercepts at plus or minus 2. Pretty easy calculation in our head. So the semicircle applies from -3 to 0, but not including the 0. Remember, these are x values. So nice open circle there. The parabola applies from 0 to 2, but not at 0. And then what is this? Well, this is really cool. This just says when x is 0, y is 0. So all that is the point 0, 0. All right, there it is. And again, this graph is discontinuous at x equals 0. Piecewise functions are notorious for being discontinuous at what I call their cut values, i.e. where one equation switches to another equation. Now they don't have to be discontinuous there. The graphs could easily meet up, but they often are discontinuous. All right? So pause the video now and write down anything you need to. Okay, clearing it out. All right, well, one more problem. All right, let's do one last problem. Had a little bit of an issue there with the memory on my computer, but I think that we're back. Hopefully it'll clear itself up. So for the last problem, what we're going to do is we're going to look at an absolute value function. Absolute value functions are very important in the course, but the irritating thing about them is that they really are piecewise functions, and we're going to see that in the next problem. So here I'm giving you the function y equals the absolute value of x minus 2, and I'm asking you to draw a rough sketch and then give an alternative piecewise linear definition for this function. So why don't you go ahead and try this? I know it's a little bit different, but take a shot at it. All right, let's go through it. So I'm going to take full advantage of the fact that I've got this sort of ability to draw lines here. And I'm going to draw some sets of axes. Okay. And then what I know is that I know that this is simply a shift of y equals the absolute value of x down 2 units, right? There's no horizontal shift here. So I'm going to just do 2 units down, and then I think I'll draw my graph in red. Okay, something like that. And something like that. All right. Now, what hopefully will make sense to people is that this is simply the line y equals x minus 2, and this is simply the line y equals negative x minus 2, right? Both of them have a y-intercept of negative 2, but this has a slope of 1, and this has a slope of negative 1. So the question now is, how do we write that as a piecewise function? Well, I think that everyone would agree that it's negative x minus 2 when x is less than 0, positive x minus 2 when x is greater than 0. The question is, what do we do when x is equal to 0? Pause the video for a moment and think about that. Where should it go? Well, there's a lot of correct answers to this question. One thing that you could do is you could just say, well, it's equal to 0 when x is equal to 0. That's one way of doing it. Or, I'm sorry, it's not equal to 0 when x is equal to 0. It's equal to negative 2 when x is equal to 0. Or, if you wanted to, you could just tag the equals right there. Or, and this is a little bit tricky, I gotta make it very small. Or, you could tag the equals right here. And believe it or not, you could even tag the equals here. Now, that's awfully confusing for people because they never see that in piecewise functions, and it certainly isn't standard. But remember, the definition of a function. Given an input, there can be only one output. So if I use this formula and put x equals 0 in, I get y equals negative 2. And when I put 0 into this formula, I also get y equals negative 2. So there's no issue putting the equality in both locations. In fact, in a certain sense, what's nice about it is it tells you that both formulas have the same output. All right, well, I'm going to clear out the text here, so make sure to write down anything you have to. Okay, it's gone. Let's finish up. So today what we looked at was the geometric idea of continuity, the ability to draw a graph from x equals a to x equals b without ever picking up your pencil. You go from the beginning to the end without ever lifting that pen or pencil up. We also reviewed how to evaluate and graph piecewise functions, and then made the connection between piecewise functions and continuity. For now, I'd like to thank you for joining me for another Arlington High School Math 4 Honors lesson. My name is Kirk Weiler, and until next time, keep thinking and keep solving problems.